I'm going to talk about how these things combine, and this mysterious thing called the state of flow, which I think some of you probably know about, but we'll review a little bit to begin the talk. So, as Focus said earlier, Clojure is a language built on deep philosophical roots, and we're all channeling Alfred North Whitehead here, since Rich used it in his earlier talk at the JVM Summit. And so we know we live in a world based on sort of deep philosophical truths in Clojure. But I don't want to talk about that. What I want to talk about today is a really important fact about Clojure. Clojure is fun. And everybody says so. You go around the blogosphere and everybody says it. You look in the ERC logs, and I've got 1,400 references to Clojure in front. There's 54,000 hits on Google. Right? Someone thinks Clojure's fun. I said it. I bet you said it too. But what I want to talk about is why is Clojure fun? And rather than delving into deep philosophy and all that stuff, which we'll get plenty of, I want to turn to pop psychology. Mihaly Csikszentmihalyi writes and speaks about this notion of flow as a way to achieve meaningful happiness in our lives and in our work. How many people know Csikszentmihalyi's work? Okay, pretty good fair. This has been very popular in the programming community because it seems to strike a nerve, and I'm going to talk a little bit about that today. Don't worry, for those of you who don't like talking about too much psychology and stuff, there will be Clojure code as we get deeper into the presentation. So I want to start with a disclaimer here. This is a really opinion-driven talk, right? I'm going to talk about my experiences, sort of how I felt about code and how I feel about how things interact. This isn't science. But as I say here, I just want to get a conversation started. I think it's an interesting thing for us to think about as we code. So without further ado, I will introduce flow to those who don't know, and maybe give you a different perspective for those who think you know. So to proceed smoothly and readily, that feels like a good thing. We think we know all about that, right? Here's a nice example from nature of flow, right? This river proceeds smoothly and readily, not a big thing. But actually there's an interesting point here that you miss when you just look at this, right? In order to get to this state of easy movement, the river has actually done a ton of work, right? The river has dug this channel over millions of years through hard rock. It's found ways through the topography that make sense for a river to flow, right? I'm anthropomorphizing the river a little bit, maybe more than necessary, but you get the idea that sometimes to get to this easy state actually requires finding the right way and making the right way. So we know about flow too, right? We've got flow charts, we've got flow of control, we've got data flow, right? All these notions from computer science have the word flow in them. So there seems to be some things mixing up here, right? But Csikszentmihalyi talks about flow as a state of being. And I'm just going to pull a couple of quotes from his book on the subject flow. When the information that keeps coming into awareness is congruent with our goals, psychic energy flows effortlessly, right? So this is sort of the opposite of being frustrated, the opposite of not knowing where we're going, the opposite of being passive, right? We have the information that we need to do what we need to do when we need to do it, and that makes us have psychic energy. And so this is what Csikszentmihalyi talks about as the state of flow. So again, here's another key quote. The self becomes differentiated. That is, I get more identity as being someone different than, say, David Liechti, as a result of flow, because overcoming a challenge inevitably leaves a person feeling more capable and more skilled. And again, this feels kind of right? As we actually do things in life, we gain a sense of who we are and a sense of our own confidence and so on, right? So what does it feel? What's the state of flow feel like? This is a sense of optimal happiness that Csikszentmihalyi talks about. And he did a talk at TED in 2004, which has been very popular. I bet a lot of you have seen it. I'm going to actually just steal this slide from that talk. And there are references that will be in the slides when they're online, so you can follow all this stuff through. Completely involved, focused. Ecstasy, and he uses this in the Greek sense of the word, being outside of ourselves and not being concerned with ourselves. We know what needs to be done. We have this clarity about what we're doing. We know that we can do it. We're not worried about things. We're not agitated. We're serene. And we don't worry about time. I think lots of programmers have had that experience. And the process itself becomes its own reward, right? We don't need to, we're not only doing it for the money, we're not only doing it for whatever comes outside, but rather just doing it makes us happy. I doubled something in my slides here, let's pop through this. There we go. I don't know what happened there. How do we find flow in programming? So now I'm going to try and connect these ideas of programming and some of the ways we think about flow in programming, and and this idea of flow that we get. So the real question is, how do we find flow and not frustration, right? We all are familiar with sort of the timelessness of programming, but sometimes that timelessness is trying to get my Linux printer driver to print my existing printer. And yes, it turns out to be 3 in the morning when I'm done and I've lost my sense of time, but I wouldn't exactly call that a state of optimal happiness, right? So we're trying to distinguish these two senses in which programming can be timeless, right? And then what can we do, both from the point of view of our language and environment, and also in terms of the way we approach code and the code we write. So Lisp has this long hacker tradition of people who've been building things. In his classic book, Computer Power and Human Reason, Joseph Weizenbaum talks about this as compulsive programming. People, and I grew up around MIT way back in the old days of AI, and so I had known a lot of these people who just couldn't separate themselves from the computer. They're in the AI lab all night. Guys like Richard Stallman come to mind. They sort of detach from humanity. And so Lisp was clearly an addictive world, right? But there were some factors in Lisp that made Lisp a really interesting environment for finding this state of flow, right? And two key ones were homoiconicity and the fact that Lisp is symbolic, right? This changed the nature of programming from what was then a current Fortran, COBOL, ALGOL world into something where the computer was a canvas on which you could express sort of an arbitrary idea. This notion of symbolic computation, the language itself could be manipulated. At the time, people were mostly using self-generating code. Now we use macros, right? But macros took an astoundingly long time to develop in the history of Lisp. But I'll leave that for another talk. And then, so the other side of this, so we have this canvas, and then we have the REPL, right? The REPL is a way that instead of, in the normal write, compile, debug cycle, the computer is a target, it's something we work on, right? In the model that works more like the REPL, and Lisp isn't the only one that has it, but because of things like homoiconicity, sometimes the Lisp version is more intense. But because of that, it's more like we're mentoring a partner in some ways, right? We can investigate its current state, its what's happening with the machine, what our algorithms are doing underneath in a very rich way with the REPL. Now, functional also has some interesting characteristics that I think push us towards this state of flow, right? Immutability, composition, and horizontal abstractions allow us to enter this world where we can really focus on exactly where we are in a problem. We can build these structures out of the same tools we always have in our tool belt and build new solutions out of mechanisms that feel very familiar to us. So I think the functional world that sort of as viewed through sort of the Haskell lens or the pure functional world as opposed to the Lisp functional world gives us some real power towards getting to flow. Luckily, it turns out a lot of people in this room probably know a language that combines these two threads, and we call that language Clojure. So we come back to the notion that flow is a feeling, right? The code is almost an extension of ourselves. We get into our code, we understand it. I think of this as sort of riding with the data and transforming the data as we go along, right? And how do you build programs that feel that way, right? How do you build programs where you feel like you're actually manipulating the data in sort of a continuous and smooth way? Again, remember, flow proceeds smoothly and readily, right? Well, one of the things that makes that happen is this feeling that we have tools on our tool belt that are easy to transform the data, right? So I would claim that the right model to do this is dataflow and not flowcharts and other models, right? And I'm try not to run off my bullets because I can't remember how many bullets I have here. You know, the really important thing here is that we have this nice granularity when we're dealing with data. That is, we're always dealing with data in about the same size chunks in a given part of our programming experience, right? So we manipulate and we move forward. Small number of unifying abstractions helps. Conditional execution should, in order to achieve this granularity, you need to box up conditional execution in first order functions like filter and so on, right? So that's sort of this notion. Let me give you an example. This ABS was a system we built back around 1990 in a functional language called C. But we really got it right with this, and I built this with Craig Upson and some other people way back when. This is a system for scientists for doing visualization of data, and it was built around some key abstractions about how scientists use data. And we reduced the number of actual data structures we had to some very coarse-grained fields, element meshes, geometries that could then be manipulated in an abstract way, right? Despite the fact there were vast differences from application to application, how n-dimensional fields were actually used, for instance, right? By doing this, we were able to give scientists this tool belt. In this case, the tool belt usually wasn't programmatic. You could access it programmatically too, but most people actually just use this graphical interface. And get animations out of very opaque scientific data. And it was an amazing thing to see. So this is the data flow model. And again, the key here was granularity, abstractions, right? So that's the dim and distant past. That's sort of the intro to this idea. Now I want to begin to talk about some examples that are real Clojure code. What I really care about in these examples is both that the way that they're created has this idea of flow, and that the way that they allow for their use encourages this idea of flow. Okay? And really I want to look at problems that have a lot of back and forth in the problem typically, right? And where the solution that was picked for those problems smooths that out and creates a nice new way of thinking about the data. So the first one I'm going to look at is a really nice piece of code that was written by Chris Hauser with help from Rich Hickey. It's in Contrib, and it's called FillQ. How many people here have used FillQ for something? Okay, so this is like zippers. This is another obscure feature of Clojure that you didn't know you had. And it's one of my favorites, so I'm glad to be able to talk about it, right? My statement of the idea is a little bit simplistic and biased based on how I tend to use it, right? But FillQ allows you to take things happening in the external world or things that may result in long computations or other things you would normally think about using some sort of concurrency or some sort of, you know, who knows what, and turning them into something we all know and love in Clojure, which is a lazy sequence. So FillQ, let me get over here so I can actually point since I don't have a laser pointer. FillQ has a simple idea, right? You have a generator function that generates new data, potentially slowly, potentially very asynchronously, and you have a consumer that wants to consume that data in a serial way. You create a FillQ by giving a generator function to the FillQ world. It then wraps that generator function in a future, calls it with the fill function. The fill function is the function that the generator can call whenever it has new data. So you can think about the generator as just sitting there running in an infinite loop. The time between loop iterations may be microseconds or maybe days. In fact, I'm going to show you an implementation where it usually is days. When it gets some data, it calls the fill function. The fill function just queues up the data that was passed, more or less, and we'll see the details later. And there's a lazy seek on the other end that's reading from that link block and queue and going to the consumer. So now we've taken a completely sort of asynchronous, worldly thing and turned it into just sequencing processing, right? We'll talk about how this works. So this, don't try this at home. I've taken all the special cases that make this actually work out. But as I think it was Christophe said earlier, it wouldn't fit on a slide if I hadn't. So we call fillQ here with the generator function. The one weakness of this in terms of implementation from Chris's point of view is the functions all kind of have the same name. But the filler function is passed in, and that's the user-supplied function that will generate the data. And then inside the let, you see we create the three elements. We have the queue that connects things. We have our filler function, or the internal fill function that the generator function will call. You can see all that does is put the passed in data on the queue, and the real implementation does a bunch of stuff in case the reader has gone away and other stuff. And then we wrap it all in a future. We call the generator function with the fill function, and so on. And then on the other side, this creates the consumer. And I can't tell you how many times I've read Clojure on the IRC saying it's almost always an error if you begin with two parentheses, but here he does, and it's not an error. So he's creating the drain function that will create the lazy sequence. This really is just creating the lazy sequence such that it can essentially recurse on itself. It's not actually recursive because it is a lazy seek. But and this is just reading from the queue. That's super simple. So this is very simple, but what it's done is it's changed the way we think about this data that comes in. And I'm going to show you a use case here. Here we have what looks like a ring app function at the top, right? And what we're going to, let me give you context, sorry. What we're going to do here is show you the code that Autodoc uses inside, so that when Rich checks something into Clojure, you get documentation 3 minutes later. And this works because GitHub actually will call my server and tell me that there's been this update to the source repository, and then I can run my build and check in the new documentation. And this is all automated. And the way it's automated is using fillQ, of course, right? Because it would be very bad if Rich checked two things in within a 1 minute period and I started building two Autodocs at once, because of course I haven't made it robust parallelism. It's just running all over its own file system. And you wouldn't like the resulting documentation. So we serialize it using fillQ, and we have an app function. Again, this is slightly simplified, but we have an app function that is a funny ring app function because it has this first fill argument, and then it takes the request like a normal ring app function would. It simply decodes the incoming JSON and pulls out this payload argument and passes the payload argument into the fill function. And then it returns and we see the fill function that we've been passed called right there. And then it returns a 200 code because GitHub doesn't care if we succeed or fail. That's our problem. Then the next thing is we have the code that is the executive of the application. The executive of the application calls fillQ with a function that just calls Jetty, right? And then, so we make a Jetty endpoint. We build the partial app fill, so fill is actually a constant by the time it gets passed over there. And we just read off this queue, right? This is just do-seq on a lazy sequence now, right? So the internet, we've converted the entire internet into a lazy seq. Well, maybe not the whole internet, but the part we care about. And then we just call the routine that actually builds the Autodoc, and that's trivial, we don't care about that. So with the resulting payload. So that's fillQ. So again, what we're looking for here is things that take this sort of rough programming with lots of special cases and lots of changes in granularity and turn them into things that smooth that out and give us a sense of constant granularity and working within the abstraction set and tool belt that we already know. Anyone who's interested in learning more about the intricacies of this can just look on GitHub. I don't have a watch here. Can someone give me a time check?
Yeah, 20 minutes.
Okay, plenty of time. Plenty of time. So the next thing I want to talk about is Ajax push. right? Now, Ajax push is one of those big issues in the internet right now. And it's one that I think some of you have actually already heard me talk about on previous occasions. But we want to create servers that can dynamically update data on clients, typically clients running inside web browsers, right? I'm going to give you an example where the client is a jQuery client using asynchronous XML requests, but I'm not going to talk about the client at all here, really. I'm going to assume people kind of know what clients do. We're going to talk about a server that can do this, and this is a clunky operation, right? It's like clients have things, I need to know what I sent them last, I'm sending them new information all the time. Do they already have some of this information? Do they not have it? How can I make that efficient? Do I need to wait for new information? Because I don't want to send them the same data over and over. That's not very efficient. And I don't want to save a bunch of dead historical state for clients that don't exist anymore and have things running out there. So seeks feel kind of wrong for this, right? And I don't really want to have to keep track of what each client I sent them and what I didn't send them. The session state is annoying. So I want to talk about ways that we can sort of meet all these goals, right? And I'm going to use as an example a developer dashboard that we did at 3VR, which is where I work, for the record. Basically, we're going to talk about one path through it. I actually use this Ajax stuff on a few different paths. But we're monitoring perforce check-ins, right, in real time. And we want to be able to show them on a big screen. And so people are always sitting around writing source code. As a manager, I wish they were doing more of it. And committing it into the perforce server, right? And the perforce server is a big legacy app. It, is just sitting there doing its thing and doesn't know anything about it. And here we have a dashboard web app that's serving out anyone who wants to observe the state of, what a particular team is checking in or what's happening with a particular release. And this dashboard web app is simply polling and using an advanced technology called shell commands the perforce server. And the perforce server tells it what's new, and it updates its internal state. And the idea here, now the good news is my team isn't so productive that this state exceeds the size of memory, so I can actually just keep it right in a Clojure structure. Obviously, as you get bigger data structures, you have to think about that a little bit. So I get an update, and the web app always has the current state of what we're doing. Now, you have clients that are doing requests and responses, right? And sort of the magic secret here, which is not that magic, is we tell the client to keep a serial number. And so we can just think in terms of serial numbers, right? And the serial numbers are really just unique cookies that correspond to each state update. It turns out they're incremented because that's the easiest way of making a unique cookie, but that's not so important. Okay, so the solution revolves around this magic three-part data structure, right? We have the sequence number, which represents this version of the state. We have the current value of the state, and we have a promise that someday we'll have a newer, better current value, right? And out of this, we can make what I call a GC-friendly pseudo-sequence. That is, things get dropped when no one's referring to them. We don't have to hold ahead. We don't have to remember any history, but we do get the advantages of a sequence, and you'll see that in a second. And it also will give us a clean interface, and we'll walk through that, right? Now, the interesting thing, when a client comes in and looks at this three-part structure, they can return immediately if the data there is new. And new means that it has a different serial number than their old serial number. Or they can wait for the next value if the data there is old. And old is a per-client concept. If I already had that data, I want to wait for the next update. And the producer itself can produce delta lists. The producer has access to the serial number information and can send minimal chunks of data, okay? So here's the first part of the implementation, and this is the function that actually does the update. And it's called, again, as in build queue, the user provides us a function, and this is the function, this update function is the function that will actually, in this case, call into the perforce system and get the new data from the perforce system and figure out what the new value should be based on the old value, which it gets passed. And we also get this sort of existing structure, which this is the current value, and again it has the three parts, the serial number, the value, and the next is the promise that it has, and we destructure it there. And so of course we do this advanced calculation, come up with a unique new serial number. Then we get the new value just by calling the user supply function and passing the old value and the serial number. He'll use the serial number for marking deltas. This is now the new serial number we're giving him, so he can use that to mark deltas. And we create a result. And then we do two things with the result. And the result is just a new triple. Actually, next goes off the right, but it's a promise called with no arguments, right? So there's nothing there. And then we do two things with that. One, we deliver on the promise. So anyone who is waiting on the old value of the state to get they decided that that value wasn't good enough for them and they were waiting on the next part, we'll see that in a slide or two, they now get the result and can proceed. And then we return the result, which will then be stored as the current state value. And that's timer stash is just to keep Java from garbage collecting on whole universe. So here's the function we call to create a new version of one of these, right? And again, when the program wants to create a new updating state, and this particular one this particular implementation is focused on polling, right? So it's based around a timer and an update time, but obviously you could come up with similar versions that were more event-based. If you had Perforce, unfortunately, it won't give us that capability, so we don't do it. When we do this, we create sort of the initial state, which is serial number 0 and a promise and no value. We know colon value will return nil if we just don't specify it, so we don't. And then we create this timer that calls that do update function we saw in the last thing. Again, that's a partial, and it's called with the current state. We tell it to run the timer right now and at the interval that the user specifies. In the Perforce example I'm talking about, you'll see this in a second. We poll every 30 seconds. Again, my team isn't fast enough to make it worth polling faster than that. And then we update the timer stash so we don't lose it. And we return the initial state to the user. Or actually, I'm sorry, we return the state reference to the user. Right? And the state reference for the user basically serves as a cookie so that he can call get next on it. Now, when new requests come in and we want to get new state, we call get next with the old serial number and this reference to the state. And then this is a really simple decision. We look at this thing and we say, oh, is it already up to, is it already new? I.e., is the serial number, our old serial number, different than the serial number of the current state? If it is, we just return the current state and the serial number because the client's going to want to keep that for next time he calls. If not, we return the serial number and a value of the next state. And again, that's a promise, so that might hang there until the next update runs. Typically it does. Typically the client will come back right away after we send them one piece of data, he'll want the next piece of data, and it's a while until the next one comes through. But that's, as we all know in the internet, that's not always true. We might miss some updates, et cetera, et cetera. So, and then here's the code that uses this for Perforce. Pretty simple. Here, I'll start at the bottom here. We create this updating state with our own update function here, and it runs every 30 seconds, right? So then, I'm not actually going to go through this in detail. This basically gets the Perforce data and builds it into just a list of maps. The interesting thing here is we add on the serial number where we discovered this particular Perforce commit as one of the elements. And that lets us, on the other side, distinguish which things are new and which aren't. And here you see how we do that. To get all the new values for a given serial number, first we do the get next to get the latest state. Again, that may hang if our current state is all set. And then we compute this new serial number by filtering through the state we have and only getting the new elements, right? So we'll end up we return the new serial number and the filter of only new stuff from the old serial number, right? So what we're getting is we're getting a delta from the last time this guy got data in our database to the new stuff. So, and then recent submit just does the stuff that it needs to get sent back. I don't have the ring. Above it is a sort of mustache ring interface to this stuff that actually does the to.json and all that stuff. But eventually what we'll get past is a to.json of this. So that is how we consume it. And here's the result. We can see here in the result, this side is actually the Perforce check-in. In real time, we're getting these and marking them, and this table just updates on the dashboard. People can watch it, see who's actually working today. And then we can trigger off some graphs and some counts, and everyone's happy that we're doing things, right? So that's how to make a non-agile shop look a little bit agile, too. So, a couple of disclaimers about this, right? Obviously, this is a threaded version, right? If you were trying to serve millions of clients through this version, you'd end up with all these threads waiting on the promises, and you'd probably get pretty unhappy pretty fast. I don't think it's a long stretch. I haven't yet done the implementation, so I'm just assuming. It's a long stretch to do a event-style implementation and rapid and allo. We have about 4 clients for this right now, so it's not really that big a deal for us. And another thing this does sort of implicitly is with long polls in HTTP, you actually want to return sometimes. The polling architecture here creates new empty versions for Perforce every 30 seconds, so we don't need to deal with that. If we didn't want to do that, we need something that had timeouts and promises don't have timeouts, or we need slightly different mechanisms. That's something to think about. Okay. So now I want to talk about Live, which is one of my favorite programs. And Christophe actually set me up really nicely earlier, and I want to talk about sort of how that interacts with this style of flow. What's really nice about Live is that the templating style separates the design of the HTML completely from the dynamic content. It uses zippers. You guys have all heard about zippers now. The morning talks are actually a great setup for this talk, I think. And the key interface, and Christophe talked about this a lot, right, is now you're using fully first-order interfaces with a little macro-oriented syntactic sugar, but a lot of the syntactic sugar is actually not created by macros. I'll talk about that in a second. And you can create what seems to be a declarative style. It is a declarative style, but you have the ability to use our whole tool belt across that declarative style, unlike something like, say, SQL, where you're leaving the language, or even a fully macro-derived thing where the syntax is driven by the DSL. I strongly recommend everybody read the source to Live. It's very mind-bending, but a lot of really good examples of idiomatic closure. So let's talk about what's magic here, right? What's magic is, first we have these selectors. These selectors are just vectors. Christophe talked a little bit this morning about how to handle those in terms of processing. But these vectors are actually functions, right? They aren't functions themselves, but the at macro that Christophe uses will see that it's a vector and wrap it in a function, right? So in fact, you can use a function there that's not a vector to do special purpose selecting, okay? So it's a really nice combination where it is functions, and therefore it becomes composable, right? Inside the function, you can then use a selector, right? And again, on the right-hand side, so all these in Live templating things are a right-hand side that's selecting, left-hand side that's selecting, and a right-hand side that's doing the transformation on the underlying data. So here, and there wasn't enough space to actually make this left and right on the top, but here we see we're combining functions. Now what's interesting is content looks like just a function you're calling that does a direct transformation, but it's actually not. Content returns a function that can modify any set of sequences of data, and depending on the selector, that content function that's returned is going to be called any number of times. What's important about that, and what makes that different from just being called repeatedly at different times, I see Christophe watching me intently, so I hope I get this right. What makes that different than just calling content several different times is because of the fact it returns a function, it's then composable. And in fact, some parts are composable themselves. Here's a simple example. The do macro return will combine the two functions it's called with and execute them both. More complex examples come with clone for, which allows you to create a whole sequence, and the function becomes a function that will actually then do the repeated thing, right? So again, composition, we have an internal function. We see we use a splat here because we are actually just sort of making a new function rather than using one of the predefined function returning functions in live. But then that uses the at macro and does a whole new selection of what's down inside there, right? And this is actually right out of the inside of the Autodoc. So if you ever wonder how the Autodoc's created, here it is. Similarly, we can make functions that are returned conditionally, right? Here, I'm working on a given namespace. It's only if it was added in some version do I fill in this content. In live recognizes nil as meaning just erase that particular part of the template, and that turns out to be really useful. So again, in live, by really working on this functions and composability of functions and creating a DSL out of functions where you might have some shorthand like using vectors or using other simple notation, you can get this composability that makes things flow much easier. And if you look at, I'm not sure build HTML in the Autodoc is the most elegant piece of code, but you can see where I leverage that all over the place to make a much clearer program, where it's very obvious how the Autodoc is getting built and how the templating is running inside the Autodoc engine. So, to boil it down, so the goal here is you want to bring your code in line with the existing abstractions, right? So where you can turn an idea into a sequence, a la FillQ, that's super powerful. Makes a lot of stuff more flexible. Makes you feel again like you're getting this notion of transforming your data, right? And it lets you get your tool belt out. Rich has given us, and others building on top of him, have given us a rich set of tools for working with sequences. Zippers are another great example of this, right? Zippers give you an abstraction in addition to sequences, but they also leverage, as Luke was talking about this morning, they leverage existing abstractions, right? And that's really important, right? We can now use not only the tools that zippers give us for doing particularly tree manipulating things, but we can use all of our underlying abstractions. We don't lose the underlying data type, right? And that makes our thinking we know how to do it, as opposed to sort of a more kingdoms of nouns approach where every class has a different set of things going on. Now we bring our whole tool belt to the job, and we have some new tools that are specific for that job. Along that line, when we build new abstractions, we really want to think about the abstraction we're building, right? And the more that we get these sort of rich extended abstractions into Clojure, the more it's going to feel like we have this data flowy, transformational, composable world, right? So again, I point to zippers as an option. I'm really glad we had that talk earlier, right? Where zippers are a really nice layer in the Clojure implementation on top of the existing abstractions. It can be composed really nicely. Working in consistent granularity. One of the things that we saw in both the Ajax example and the FillQ example is the ability to turn events into things we can work on one at a time, right? And keep each of those things as a level we're processing. So in each part of the system, we have this consistent granularity. I think Clojure really encourages doing that in a nice way, right? It's sort of natural to work with a consistent granularity rather than in a more Algol style language where you tend to sort of go back and forth and you're accessing some field of some class, etc. Right? Be aware, right? I mean, a big part of reaching this state of flow and reaching this happiness, especially in programming, right, is to be aware of the way you're approaching it and how that affects your mental state, right? I mean, programming, we want programming to be fun, right? We have a lot of tools to make it that way, but it's up to us to remember to do it. And read good code. So that's what I have. Whoops. I think just because I'm on the discussion slide, I don't need the microphone anymore. That's what I have for today. Do we have time for Q&A?
Let's do it out in the lobby.
Okay.
So time dictator strikes again.
Okay, cool. Ha!